we're happy to have Vivek Shende from UC Berkeley, but now on a different connected component, Metagli flare in Sweden, Sheaf quantization of Weinstein symplectic manifolds. Go ahead.
Well, I should correct you. At the moment, I am also from the Syddansk Universitet in Denmark.
All right. So, well, 3 is better than 2.
Yeah,
so.
also there.
Okay, good. Okay, you can start.
Okay. So today I will be explaining to you about the microlocal sheaf theory. And I will, some sort of elaborate construction using this, but let me begin by just explaining a little bit about what this is. And so this is a subject which, if you want to read the original texts on, you should read Kashiwara and Shapira. This is a subject that was pioneered by these guys. Let me try and give just a little bit idea about what it's about. So the ingredients are sheaves on manifolds, which is the name of their book. And so, for example, let's just start with an example. So my running example for a while is I'm going to take the manifold to be the manifold R2, and I'm just going to try and draw you some sheaves on this manifold. So here is a kind of sheaf. This is my attempt to draw the constant sheaf. So by the way, just in case you don't know what is a sheaf is something which assigns some, let's say, vector space or chain complex or something to every open set. And if you have a smaller open set, then there's a restriction map. So maybe this is not such an interesting sheaf, but already a bit more interesting example is, so maybe I'll draw the others on, sorry, too. A bit more interesting example is if I take a sheaf, which is maybe the constant sheaf supported on the lower half plane. So I'll write this as K on the R cross R less than or equal to 0. So this is another sheaf, also on this manifold. This sheaf has the kinds of things you want to think about when you think about a sheaf is you want to think about what is its sections in different places. And what value does it assign certain different open sets? And here are 3 kinds of interesting open sets. There's this red open set. There is this blue open set. And there's this green one. Oh, that was the eraser. This green one. And we can discuss what value this sheaf takes on these open sets. And you know, on 2 of them, you don't have to think very much at all. On this blue one, that's in the place where the sheaf is non-zero. So of course, here it takes the value K. And on this red one, it takes the value 0. And now you have to think carefully about what value it takes on this green one. And hopefully the answer is also 0. I think that's correct. There's some participants in the audience who will be able to correct me if I've said the wrong thing there. It's either 0 or K, but it's one or the other, and hopefully it's 0. Oh, by the way, feel free to unmute yourself and ask questions at any time. I'm perfectly happy to take questions as we go along. Jan, are people able to unmute themselves? Is that?
Yeah, no restriction. Okay.
Yeah, so if you feel free to ask questions. So now let's make a bit more interesting example. So here is this kind of, I've drawn this, what's called the front of the unknot. And this is maybe the first example to think about somewhat seriously. And we're going to think about something which is the constant sheaf in the inside and the constant sheaf, let's say, along the top, but 0 along the bottom. So just to indicate that, maybe rather than draw 0 along the bottom, the convention is that you maybe draw a dashed line here. Okay. So this is another example. And again, let's draw the various kinds of open sets that we might have. Now there's a few more. So as before, there's the maybe easiest kinds. You have the ones on the inside when the sections of the sheaf are just the field. The ones on the outside when it's just definitely 0. And then you have a few different kinds of these green ones. You have maybe this one, and this one. And of course, at this top one, I guess you can't see where I'm pointing, but at this one over here, the picture is like it was in the previous picture where I wrote 0 before, so it's 0 again there. And by contrast, at this bottom one, I'll explain to you why in a moment. Here it's a bit different, and the stock is in fact k, and the sections are in fact k. And here on the outside corner here, it's also 0. Okay, I haven't told you yet why that is or how to calculate it. That's just a true fact at the moment, which you could, if you wanted yourself, go home and calculate from the definitions. But now let me say, I gave these examples because I would like to explain to you how a microlocal sheaf theorist would think about these examples. Okay, I mean, like I said before, you could just calculate from the definitions, but to think about it, it's better if you think in terms of two notions which are very closely related. One is called the microsupport, and the related notion is called non-characteristic propagation. So let me explain to you what these things are, and then I'm going to then explain, we'll come back to these examples and I'll explain how to easily compute those sections. So first of all, the microsupport. Just what kind of thing is it? Microsupport, it's to a sheaf on a manifold M, it assigns a subset, a conical, a closed subset of the cotangent bundle. So that's the kind of thing it does. And the definition of it, well, it's kind of a local definition. And I should tell you what to do at a point on M. Okay, so I have some point on M. And on this manifold, I have some sheaf that's going on. And I would like to know if some particular covector, let's say this one, is in the microsupport or not. So is it in the microsupport? And the way you study this question, I mean, what the definition tells you to do is you make first a small ball around that point. So this looks like kind of a big ball, but you should think of it as a small ball. And you make, you take the, you know, what a covector really is it's really a foliation by hyperplanes, and you take that hyperplane. And you take the things on one side of that hyperplane. And then you compare, so there's some sheaf F living here, and you compare the F evaluated on the red region to F evaluated on the yellow region. That's the, as I told you, that's the one thing that you're allowed to do with a sheaf. You are allowed to restrict it. Okay, so that's a map you could consider. And you ask the question, is this map, so if this map is an isomorphism, is not an isomorphism, let's keep it in the page. Then this covector, this yellow covector, is in the microsupport. Of F. Okay, so the job of the microsupport is it tells you in which sort of directions the sheaf is changing. So let's go back and reconsider our three examples above. So in the first example, we had the constant sheaf. And so I can ask, you know, is some particular covector, maybe this one, is it in the microsupport? And then what I'm supposed to do is I should make this red ball, and I should make this half this yellow ball, and I should consider the restriction of the sections over the red ball to the sections over the yellow half ball, and ask, is that an isomorphism? Of course it is, because it's the constant sheaf. So the restriction is an isomorphism. So this vector is not in the microsupport. Okay, so and of course the same would have been true for any at least non-zero vector I took. I haven't told you about when zero vectors are in the microsupport, never mind. So at least any non-zero covector would not be in the microsupport. So let's look at the second example. So this second example was like this. And you know, I had written above, and let's consider, contemplate two different situations. I should compare, let's say, this one. I should think maybe about this one. I should think about this one. And what does that mean I should think about? I should think about the restriction of this red ball respectively to this, let's see. To this yellow ball or this yellow ball. And I told you already what are the sections on those kinds of things. I told you it was 0 if it sits above, and the sections over that whole thing were also 0. So when I restrict the whole thing to what sits above, this one is an isomorphism, so this induces isomorphism. And that means this one is, so it's not in microsupport, whereas this one does not induce an isomorphism. And by the way that those of us who work in this subject, the way we like to draw this situation is that we will draw the microsupport directions like this. So these are the codirections which are in the micro. At each point, I've indicated the codirections in the microsupport. So here, the microsupport is, you know, the negative codirections. Negative, let's say. Well, anyway, I drew what it was, so maybe I won't write it. So the way to think about this picture I just drew is that well, you know, while I was at it, let me leave an exercise for you. I did 2 of the directions, up and down, but you could also think about some kind of like slanted direction. And an exercise for you is that this slanted direction, it's never in the microsupport. So the way to think about this picture that I've drawn is it's really the picture of what is in fact you should think of it as a Lagrangian in this cotangent bundle. Or I prefer, sometimes it's easier to think about just this yellow part, it's a Legendrian. So I was only discussing the stuff away from the 0 section. And so I promised you it was conical, and so we may as well only discuss it in the cosphere bundle. And so you can think about it in there. And the point is that when I want a Legendrian in the cosphere bundle, well, the moment I've drawn a hypersurface in the plane, like this one, this line here, it's a hypersurface. The hypersurface. Then if that's the image of a Legendrian in the cosphere bundle, there's only 2 possible choices I could pick for that. 2 possible Legendrians it could be: the positive covector lift or the negative covector lift. I mean, I have to take one or the other of the orthogonal directions. And so this like yellow downward hairs, even if they haven't drawn them so precisely, you interpret them as meaning I've taken the negative downward lift. And so finally, I wanted to draw the last, go back to that last example. This is somehow the most important example, maybe in for this talk, at least in the subject, which is this unknot. I drew it like this. And for this one, of course, I've already computed the codirections at the top of it. And it's going to be the same as this calculation I did for just this line by itself. And now I owe you a calculation of the codirections at the bottom. And I promise you, I mean, you can try it yourself, that they look like this. Okay? So it's downward on both sides for the thing which is the constant sheaf in the inside, and the inside and up to the top boundary, but 0 on the bottom boundary. Actually, it's worth giving maybe 2 other examples to contrast and compare this with. I could have the thing which is the constant sheaf inside the circle, somehow up to but not including its boundary, or the constant sheaf on the circle up to and including its boundary. And if you were to do the calculation, you would discover that this one has outward covectors, and this one has inward covectors. So basically, when it includes the boundary, it has inward covectors, and when it does not include the boundary, it has outward covectors. So that was my crash course in this notion of microsupport. I just drew you these kinds of pictures. And then I promised I would explain now what is non-characteristic propagation. So let me do it. So some people call it non-characteristic propagation, and some people call it non-characteristic deformation. So maybe just a bit of etymology. This word characteristic in this context, we borrow it from differential equations, and it has to do with these covectors, these microsupports, and specifically with the phenomena of them colliding. And so non-characteristic propagation or deformation, it means maybe not always the most, it's not a word with a precise definition, but what it means is you are varying the picture in some way so that these covectors, they never collide. And there are precise statements, of course, that you can make. But the general principle is that, so the principle is that nothing changes except when covectors collide. And the example of this principle is what's usually called the non-characteristic propagation lemma, which says that, so in particular, well, let me just draw what it says. Okay, so I'll draw what it says in this example that we've been carrying around. So now, rather than draw this dotted line, I'm just only going to draw the covectors. So suppose someone told you that you had a sheaf with this microsupport. Okay, they didn't tell you what the sheaf is. They just say the microsupport of your sheaf is this. And you ask, like, what could you know about this sheaf? For example, you might like to know what is its, what are the sections over some open set looking like this. And the way you do this is the following. You say that the sections sections of F over this open set well, that's equal to Hom from the constant sheaf on the open set. Oh. To F. And by the way, whenever I make any statement whatsoever, it's always derived statement. I always work in the derived category. So just saying that. So sections of this thing is the same as Hom from this one. And so what that means I should do is I should study Hom between two sheaves. One somehow mystery sheaf, which lives on this, this guy. And one, the sheaf which lives on this guy. And I told you that on this one, the covectors point out. Okay. And the way you compute this is you observe that this red, can you see this red? Is it possible?
Yeah, it's visible, yeah.
Okay. Let me draw this open set a little bit more somehow. Let me draw it more like this. So you can see that if I take this line and I pull it to the right, then at no point.
This is barely visible, I should say.
Okay, well maybe.
Red on black, it's not the best idea.
Okay. Maybe I'll stop using the red one so much. Oh no. If I take this line here and I pull it right, then there's two things to observe. One is that in the process of pulling it right, the red never meets the yellow, right? It's going to be green now because it was not visible as red. So it winds up here. And at nowhere in the interim did it ever meet the yellow. Because the yellow, wow. It really takes some practice to use this thing. The yellow, it's all pointing down, and the green is all pointing sideways. So one never met the other one. And what we learned is that the sections over the, but by this picture, hence the sections, so we can pull this right without meeting this one. And the conclusion of the what the non-characteristic propagation lemma tells you is that the sections over this original red one, over the red one, equal the sections over the green one. Okay, so so maybe I shouldn't say hence because I didn't state the non-characteristic propagation lemma, but this, and let me say that non-characteristic propagation, just what it means is this fact. That whenever you can deform in the way that I did without meeting the micro support, the sections stay constant. That shouldn't be so surprising because the definition of the microsupported in the first place was where the sections don't change. So somehow you just have to prove this non-characteristic propagation lemma, you somehow have to integrate the definition of the microsupport. So are there any questions now about these two ideas, about microsupport and about non-characteristic propagation?
Yeah, then you probably can go on if people
Okay,
are silent.
Continue. So okay, so that's that was some kind of background. And now let me make the basic definition of the category of microsheaves. So if you have M, if you take M of a manifold, then there's a category, there's a sheaf of categories. This is going to be a sheaf of categories on T star M. And you know, as usual, when making a sheaf, I first define a pre-sheaf and then I sheafify it. And the pre-sheaf, if I want to know what it is on some open set, this is an open set in T star M. By definition, I take all sheaves on M, and I divide it by okay, that's by those sheaves with microsupport only outside U. Okay, that's it. That's the definition of the category of microsheaves. And in particular, there's a related definition, which is, so if I take a subset, let's say lambda, either of well, maybe I'll just say it this way. Maybe the easiest way to say it is that the notion of microsupport, it makes sense for also microsheaves. And we define, if I put a subscript, let's say lambda, this is those ones with microsupport in lambda.
Lambda is Legendrian or Lagrangian, or any.
It could be any, but first of all, this notion, it really only depends. Let me assume it's conical. It only really makes sense to say it, may as well make it conical. Okay, so this is define for lambda conical. Like this, and then, you know, there's some sort of remark, which is that if lambda is disjoint from the zero section, then you may as well only remember, may as well only think about lambda intersect the cosphere. Now, this definition, I made it for any closed set lambda, or maybe just any lambda, but usually we think about it. So we usually think about this. We usually take lambda, either Lagrangian if it lives in the cotangent bundle, or Legendrian in the case in brackets, Legendrian. Okay, so
yeah, maybe one comment or question. So you work on C infinity, which means your ground field is a field of real numbers, but in fact you can sort of generalize. Yeah, there is this Bailenson Saita story.
That's true. You could contemplate doing this.
And just for number theorists.
Contemplate doing this in this Bailenson setting.
Yeah, okay.
I have not contemplated it. But let me make a remark, which is that what makes this whole theory work is this non-characteristic deformation lemma. And I don't know what exactly, how to formulate the analog in this Bailenson Saito setting.
Yeah, over complex numbers, it has nice incarnation in terms of differential equations and non-characteristic directions. But in general, yeah, I don't know.
Yeah, somehow it's important to me to be able to draw this kind of picture, at least. And so it would be good to have a way of thinking about what is the analog of this picture. Like this particular picture, it'd be good to have a way of knowing what is its analog. Okay, so this is the category of microsheets. And let me make some kind of hopefully illustrative remark example. So consider this. Okay, I should correct my drawing so it's. Consider this picture. And I want to study sheaves with, let's say, this kind of microsupport. Well, if you start thinking about it, if the sheaf has this kind of microsupport, then it will have some stalk A here, everywhere in that region, and some stalk B everywhere in this region. And because it has the microsupport it has, it's not difficult to convince yourself that there have to be morphisms like this. And what from these, where the composition of any two in a row are the identity. And what these morphisms, so the exercise is that A must, you can see from this that A must be a direct summand of B. And B must be a direct summand of A. Okay, so if you were to contemplate this example, you would learn that in fact the only such sheaves are the constant sheaf. And being the constant sheaf, in fact, this Legendrian I drew was never in the microsupport at all. So in other words, the consequence of this exercise is if you study sheaves, well, let me say it this way. If I study mu sheaves free of this particular Legendrian, well, this is 0. However, maybe I don't want to make that statement. Let me say something else. Let me say that the following thing is true, that sheaves microsuploided on this thing, let's say this thing union the 0 section, R2, this modulo sheaves just microexploited on the 0 section in R2, that this is 0. Okay, that's what my calculation should just show you. However, in fact, mu sheaves of this thing is not 0. This is, if you compute it, the isomorphic to vector spaces. Mod K. So this is an exercise to understand what is going on here. I won't do it in detail. And what this exercise teaches you is it teaches you that what mu sheaves knows about is it knows about it doesn't know very much about the embedded symplectic topology of the Legendrian inside the ambient space, but it does know about the, it only knows about the somehow intrinsic symplectic topology of the item. Okay, and so now, now I can more or less tell you what category that we want to study, what category to study. So a definition. So if W is a Weinstein manifold, and I'm to write lambda in W for its core, and just to make things simple for the moment, so this is the simple case. I assume that W is embedded in a co-sphere bundle as a codimension 1 hypersurface. That's what makes it a simple case. Then we study the category, we study mu sheaves, what did I call it? The mu sheaves lambda. And well, that's a sheaf or co-sheaf, depending on your point of view, of categories on lambda. And maybe what we especially study, and especially its global sections. So this is the category to study.
So it's a definition of this category. You consider an embedding in the cospherical bundle. Probably proves that nothing depends on the embedding.
So let me make some remarks. So remarks. It is not hard to see that this is independent of the embedding, and similarly not hard to extend to not necessarily, let's say, arbitrary Weinstein manifolds. All you have to do this is you embed in a higher codimensional space, a higher dimensional space, and thicken appropriately, and then there's somehow classical results tells you that you can get from one to the other. So that's not hard to see. But what is hard to see, so maybe not easy to see, is that it's independent of the exact symplectic form, the exact primitive of this symplectic form. You see, this category, it's supposed to only depend on W, and so maybe I remind you just briefly what is Weinstein manifold. It's a exact symplectic manifold. In other words, I have not just a symplectic form on W, I have a one form, which is the primitive of the symplectic form. And that one form, which is the primitive of the symplectic form, is what determines this lambda. And it's not at all, and if you change that one form while keeping d of it the same, this lambda, it can change very violently. And as you saw, my definition of this mu Sheaf's lambda, it was in no way apparent what should happen to it as lambda changes. So yeah, what's not so easy to see is that this is independent of the primitive. And another thing, so that's another thing which is not easy to see is that Lagrangians in W give objects of this mu Sheaf's. And the let's just say why first of all, why would we want it to be true that Lagrangians at W give objects of mu Sheaf's? Well, the reason for that is that behind this whole discussion is the existence of, I mean, there's something called the Fukaya category. It's assigned to a symplectic manifold. It assigns a category to a symplectic manifold, and its objects are Lagrangians. And we're trying to make making the Fukaya category and computing in it is hard. But on the other hand, I gave you in about, I guess, 45 minutes or so, a complete definition of this category. So, and in fact, I sort of, maybe showed you what kinds of things you have to do to compute in it. It's not so hard. And so we would like to use this category instead of the Fukaya category. And so the kinds of things we would like to know about it is, well, that it's a symplectic invariant, and that you get what makes the Fukaya category useful for geometry is that Lagrangians give objects. And of course, maybe somehow even less easy to see is that this mu Sheaf's lambda, in fact, is isomorphic to the Fukaya category W. So let me now comment about these. These are true facts. So this first fact is it's due to myself and David Nadler. I'm going to explain to you now a little bit more about it. Nadler. Myself. And this second fact This is this long series of papers of John Pardon and Shil Ganatra and myself. This GPS. And so I won't talk about that today, but let me now, having given this kind of introductory discussion, say a little bit about what goes into this into this work with David Nadler. So there's maybe two fundamental ideas in this work. So ideas. And the first idea is what we call gap specialization. And the theorem about gap specialization is that it induces fully faithful functors. And the second idea, actually, this is maybe, but in some sense, both ideas. And so let me just try and tell you what is gap specialization. So so let's say a definition. If I have so let's say given a family, given a Legendrian, given lambda in its cosphere bundle, I'm going to write let's say L of lambda. This is the length of the shortest self-Rabe chord. In other words, if you look at the geodesic flow in M, it's the shortest time it takes to get from lambda to itself. So let me just draw some pictures. So for example, if I had this picture, well, here's how the codirections are pointing. And a Rabe chord is something when I start out going in a codirection and I come back to something also going in that codirection. In other words, from the Legendrian to itself, this Legendrian has only one Rabe chord, and L of lambda would be its length. Okay, so and we say that a family lambda T of Legendrians is gapped if this length of lambda is bounded away from 0. And so let me explain about the significance of this notion of gapped. So and typically what the word comes, I mean, the place where this word is most frequently used is, again, in analysis, there's a kind of operator. And the operator has a spectrum and some eigenvalues. And you're particularly interested in the 0 eigenvalue, the 0 eigenspace. And you know, like if you vary the operator and no other eigenvalue ever comes close to 0, well, somehow by some kind of continuity, the dimension of this eigenspace remains the same. And so this is what's called gapped in analysis, and we use the notion in a similar way. So what theorem is that if, well, some technical assumptions, which I won't now describe, lambda t is a gapped family of Legendrians, possibly singular, then the limit, then there exists a functor which takes mu sheaves on lambda t to mu sheaves on the limit of, somehow maybe let's say t goes to infinity of lambda t, which is moreover fully faithful. Okay, and let me so let me just explain how. So this is in some sense the main theorem of that paper with David Nadler, and let me explain at least how you use it to do geometry. So example of this theorem is that if W is a Weinstein manifold, and let's say it's embedded in this cosphere bundle as a codimension 1 hypersurface, and I have its core and let's say I have L, a Lagrangian, let's say smooth, why not smooth Lagrangian in W. Then what I do is I take W times R. Well, this is a contact manifold. And I lift L to a, of course, I missed an important word here. It should be a smooth and exact Lagrangian. And being exact basically means that it has a lift to this contactization. And the point is, and I study, so this L is a smooth exact Lagrangian in W, and I can flow it down to the core by the Liouville flow. So LT, the flow to core by Liouville. So that's some family of Lagrangians, and I have the corresponding family of Legendrians, LT. And I claim that this LT is gapped. So this LT tilde is gapped. And the reason is that there are no Rabe choroids at all in W times R from LT to its, a Rabe choroid from LT tilde to itself, so a Rabe from LT tilde to itself, well, that would be the same as a self-intersection of this L T. And this original L was smooth, so it didn't have any self-intersections in particular. So this is gapped, and as a consequence, so hence, by the theorem, we get a map from mu sheaves of L to mu sheaves lambda lambda. And it's a basic calculation, which I didn't have time here to do, that mu sheaves of L is nothing other than local systems on L. So by this theorem, I produce for you a functor from local systems on L to mu sheaves lambda lambda. And importantly, I promise you that this functor is fully faithful. In other words, if I take, for example, the constant local system on L, and I take endomorphisms of it, it'll be the same both in loc L. In other words, e.g., so if I take the constant local system, then hom. Okay, I'm going to give this functor a name. Okay, it's going to be called psi. Hom of hom in loc L of CL. Well, this is certainly nothing other than the cohomology of L. And hence, by full faithfulness, hom in mu sheaves of this object, which I promise you, this is also, well, I guess this one is also equal to the same. And so that's how this gap specialization theorem gives you the existence of Lagrangians. And similarly, we get invariance by flowing somehow one skeleton into the other. Well, I think that is unfortunately all I think we have time for. This is supposed to be 1 hour talk. Is that right, Jan?
Well, you can go over the time. I mean, it's virtual talk, so people can leave without disturbing others. So.
Well, maybe let me say, maybe I'll take any questions now, and then I'll maybe say a few more things afterwards.
Yeah, if you have time after that. All right. Well, first of all, thank you for the main part of your talk, and now questions. So you can unmute yourself. So I see like 25 participants, including your iPad. So let's exclude your iPad. It cannot ask questions, so the rest. Okay. I do have some questions, but I would like people. All right, so maybe let me. So one question actually about your very last phrase. No, there is a question in the chat, but you can unmute yourself and ask. You are unmuted. Okay, let me read it maybe. There's some way to see Maslov data. It looks like that guy read your paper, Maslov data on L, like the classical theory of microlocal sheaves.
Yeah, so the answer, I've entirely suppressed that here. And in fact, the answer is yes. And moreover, some things I said were strictly speaking not true because I did not describe how to take care of the Maslov data. In particular, the equality that I wrote, maybe the only thing that I said that was not true is this equality. And this equality depends, this is, what's actually true is that this is a category of twisted local systems. Actually, this is twisted local systems.
What square root of the?
And maybe I'll say in a second something about the twisting. and how it arises. It's twisted local systems and twisted by some Maslov by some kind of Maslov abstraction. And the place to read precisely about this is section 10 of my paper with David Nadler. But let me just say something about this kind of Maslov business and how it arises in this presentation of the theory. So what I explained here, I was always working under this simplifying assumption that the Weinstein manifold was embedded as a codimension 1 hypersurface. But in general, no one promises you can do that, but the H principle, it promises you something else, which is that you can embed W always into some sufficiently large contact R2n plus 1, which I can put inside the cosphere bundle of Rn plus 1. And so I can eventually do it after some kind of thickening. And so I have my lambda comes along for the ride. But this lambda, so lambda inside R2n plus 1 is will be very subcritical, isotropic. And so if I tried to consider mu sheaves lambda lambda, this would just be 0. And in fact, there was no need to take sections, it's just identically 0. And to correct that, so to correct this, we need to thicken lambda by so W, it's a symplectic manifold, and so it has some kind of symplectic normal bundle, and I should pick especially lambda also, I should pick a half-dimensional space of that symplectic normal bundle in order to promote lambda to a Legendre by half-dimensional space in the normal bundle. To make it Legendre. And the choice of this space, so the existence and choice of this space is what ultimately has to do with Maslov data. And there's and somehow corresponding choices for the Lagrangian, for other Legendres. Because the point is that once I pick this data, once I pick this data on W, then if I have some L in W, then in a neighborhood of L, the neighborhood of L always looks like its cotangent bundle, and the cotangent bundle has some canonical choice of polarization. So once I pick the Maslov data on W in order to define the category, picking this half-dimensional space and so on, then I need to, on L, pick how to compare the polarization coming from W and the intrinsic polarization from L. And that's another choice, and that choice is what's classically called Maslov data on L. But for, in fact, this business of picking a half-dimensional space in the normal bundle, you need a lot less than that. But to explain the sense in which you need a lot less than that, I have to go into a little bit of homotopy theory, and maybe it's better if you just look in section 10 of that paper.
Okay. Okay. So in the chat, he says, thank you, which means that he is satisfied with your answer. All right. Maybe more questions? All right. So I have a couple of questions about sort of generalizations and applications. So you said Weinstein, and but as for Liouville, you cannot go.
Well, so maybe let's discuss that a little bit. So you can ask, where did I use Weinstein? And the answer is that I used it most seriously in here.
Yeah, so very instructive.
So let me, I won't, it's a sort of very long story what kind of technical assumptions those were, but I would very much like someone to remove them. And I wrote somehow a long apology for those technical assumptions in the paper itself. So let me just give you a reference to where you should read in this paper if you would like to try and remove these technical assumptions.
Okay.
So I should say, defining the category itself, there's no problem for the Liouville part, but proving invariance and showing Lagrangians gives objects and this kind of stuff, that I at the moment only know how to do for in the Weinstein setting.
Yeah, I mean, if you claim, if you want to apply it to the skeleton, then I don't know whether it's proven for the there are Liouville manifolds without.
But I mean, I could take microsheaves on the skeleton, whatever it is.
Okay, yeah, all right. So you don't assume that it's sort of singular Lagrangian and can be anything.
In order to define it, it can be anything. But somehow in proving the various theorems, the fact that it's Lagrangian or close to Lagrangian is used.
Yeah, as for H principle, do you need, I mean...
No, not for the H principle.
Okay.
Yeah, so it's only in proving these invariance things. So the place you should look if you want to think about removing these hypotheses is this kind of long remark, remark 7.6. I mean, that doesn't explain, you know, you have to read the whole paper if you want to understand why we use the hypotheses. But once upon a time, we had some kind of approach which didn't so obviously run into these problems of needing these hypotheses. And I explained in this remark what that approach was and why it runs into trouble. And so if you want to generalize it to the Liouville case, maybe the first thing to do is read that remark.
Okay, and next sort of couple of questions. It's about a complex manifold case when, in fact, you work not in C infinity, but in the holomorphic setting, which I believe this Kashivara and Shapira had in mind, because, yeah, so what do you get then?
So
like, for example, the skeleton, I mean, this, and I mean, it will be Will it be like complex, singular complex Lagrangian, or what?
Let me make a few comments. The first is that maybe this is a question rather than a comment. So question. Question. Given the answer to this question may be known to experts. I don't know the answer to this question. But so given a, let's say, complex symplectic manifold, and let's assume, let's say a C star invariant. I mean, C star scales, I shouldn't say invariant. The typical situation is C star scales the symplectic form. Basically, most examples of interest to geometric representation theory of this kind. So e.g. Conical symplectic resolution, or let's say Hitchin system. So the question is, given such a thing, does there exist an embedding into some cosphere bundle? And of course, here I'm interested in if there exists complex analytic embedding and symplectic. Okay, this is this would be very useful for me to know. This would be very useful for me to know because then I could get started with this idea of, well, let me just say what, this is question 1. And so if yes, this would allow me to think about, microlocalizing D modules, for example, along that thing, or microlocalizing Sheaf's C constructor. Of course, there'd be no difference. So if so to the so if yes, if or when yes, so you expect that microlocal Riemann-Hilbert gives an isomorphism between how to say, like DQ modules supported on the core and mu sheaves as I've defined it right now. It would be almost a corollary of microlocal Riemann-Hilbert with to the extent that microlocal Riemann-Hilbert is somehow well-defined theorem, and one has to worry maybe a little bit about whether or not C star equivariant,
it's something is either excessive or and yes,
that somehow and the place to see what is this, I mean, the C star DQ modules, you should look in Kashiwara-Rukie. So I think whenever one can somehow, incidentally, you can probably bypass this this need for an embedding in the cases. In every case I know, the thing is actually a symplectic reduction. So you can probably, in those cases, bypass the need for an embedding by using microlocal or even Hilbert before symplectic reduction, and then using reduction commutes with quantization or something.
Something I don't like something in this idea because, well, I understand that part of your kind of basic philosophy was to get rid of counting of these pseudo-holomorphic disks in the Fukaya category. It's just everything microlocal. So
yeah.
Many people thought about that, Maxim, Tamarkin, and many others. Yeah, all right. But if your complex symplectic manifold is not exact.
Oh yes, then I mean, then of course I personally have nothing to say in that case. But the C star scale symplectic form I built exactness in.
Yeah, but this sort of excessive.
Yeah, I mean, one can prove better theorems. I'm just telling you which theorem I can prove.
Yeah, I mean, I think we talked about that a few times before. So there can be a kind of opposite, I mean, more pleasing symplectic topologists approach that you have Fukaya category, which you can compute in terms of microlocal sheaves in the case when you have Weinstein manifolds. And so this is just the answer, but the kind of bigger story, which is true beyond the exact case, it's when you really have to count pseudo-holomorphic disks, but then from the perspective of your question 2, you can indeed just embed your category of DQ modules without C star, of course, to the Fukaya category. So there is a faithful functor if you drop the C star. But if the Fukaya category, it has much bigger because it has pseudo-holomorphic disks which are not visible from the point of view of DQ module. So that's what I mean. That so okay, I understand that you basically your technique is designed for the exact case only. All right. What about mirror symmetry? There are interested people, I'm pretty sure.
Yeah, well, I mean, what this whole business was, and this GPS business and all of that was meant to support is, there's the work of Fang, Liu, Truman, Zaslow, and many people after them about mirror symmetry for toric varieties. And I think maybe some of the people after them include Kuwagaki. I think Peng worked on this also. So, and this what these people did is they proved theorems in microlocal sheaf theory, which one can translate into Fukaya category statements. And also there's my work with Benjamin Gamage. And the relationship of this kind of works. This kind of works. They happen primarily. These are calculations of microsheaves, and these calculations are comparatively easy calculations of microsheaves. And now you have you have a ways to go to get to the Fukaya category. And let me just say how what I explained today fits into that business. So the first thing is that before, what let these FLTZ and Kuigaki and also Peng, what let them work at all was that they were working in something which was already living in a cotangent bundle. So, you know, this first definition of microsheaves, it happens in a cotangent bundle, and you know, you study there. But then with Ben, we wanted to work, and with Ben, we were then working in cosphere bundle. But if you want to go a little bit further, so let me comment about this work with Ben. So what we did with this work with Ben is we, maybe one way to say it is we glued together this FLTZ construction. But we glue it in some kind of simplest possible example. And there's a much more general example one can do. You can sort of glue it together in the generality of this Gross-Siebert program. So let me call it this Gross-Siebert program. If you study this large complex structure limit, you end up with like toric varieties glued along toric varieties. And if you want to think about mirror symmetry, you should think about the mirrors to toric varieties glued along the mirrors to toric varieties. And you can do it in the generality of this Gross-Siebert program. But then the item you have, it no longer lives in a cotangent bundle. And so you would like a place for it to live. And the place for it to live, well, for example, when you glue together these mirrors of toric varieties, glued along toric varieties, mirrors of toric varieties, you know what the skeleton of that is, and you know what the thing is a Weinstein manifold. So it's somehow, you're in good shape to apply this theory I explained today. And it is almost a tautology that it has a tautology given these two works that I've mentioned so far, that it has the correct category, the category which is equivalent to these toric varieties glued along toric varieties coherent sheaves. So that's why you might like to study from this microlocal sheaf point of view. But of course, you know, mirror symmetry, you'd like to think it's about the Fukaya category, and the way you get from one to the other, let me just, I'll just say a few words about it. The point is that this GPS, so this here is, to go here, you need this work I described today, this Nadler work, and you also need these various GPS works. And what the work I described today has to do with it is that what we prove in GPS 3 is that we prove something in cotangent bundles. We show that the Fukaya category of a cotangent bundle with some particular stop is isomorphic to the category of sheaves with this stop. And to upgrade that to a statement about any Weinstein manifold, we use a trick. And the trick is the following. It's that using somehow some of the ingredients of what I explained today, it's possible to construct, so there exists, let me say it this way. So given, maybe I don't need to write this again. Given lambda, there exists something called the double of lambda with the property so such that mu sheaves lambda is isomorphic to sheaves microsploited in the double of lambda. And the basic picture of this, the picture is that maybe I'll draw a few different pictures. So okay, one picture is, so here is m, and this whole thing is t star m, and here is lambda. And making the double of lambda, I just take another one. And why should sheaves, this is not an isomorphism, this is an inclusion. But it includes fully faithfully. Why should mu sheaves of lambda be sheaves on the double? Well, the reason is that mu sheaves of lambda somehow geometrically is the same as mu sheaves on this this item lifted to the cotangent bundle. And now I can consider this family where I flow it down. And ultimately, I get this. And mu sheaves on this now conical object is just the same as sheaves microsupported in here. And so this is what's called antimicroequalization. And in fact, it's an example of the theorem on gap, it's an example of the statement of the theorem on gap specialization, but actually we have to prove it first. So we prove by hand this antimicrolocalization, and then we use it to prove gap specialization. And let me just comment about, so the reason I started out this talk doing this example of the unknot was to explain somehow the idea behind the proof of this antimicrolocalization. And the idea behind the proof is that we consider, when you want to consider some lambda, what you do is you consider the somehow lambda times something which looks like this picture, like this kind of front that I was drawing in the beginning. And the point is that if I consider maybe it's a bit too long to go into, but the way that's the best way to say it. I consider now sheaves. I consider sheaves micro-supported in this picture. And now if you contemplate what the category of such sheaves is, I consider sheaves micro-supported here, which may be 0 on the outside, so zero outside. And you remember that by somehow purely sort of non-characteristic propagation arguments, I was able to explain that the sections, for example, here should be 0, but the sections here should be somehow isomorphic to the sections here, and so on. By somehow purely geometric arguments in the beginning of the talk, I explained that. And as a consequence, when you contemplate this picture, you learn by the same sort of arguments that mu sheaves lambda lambda is isomorphic to sheaves on this whole plane. How to say? I'll just denote this like this.
So what is it?
Sheaves microsupported here. Maybe I'll write like this. So and this is somehow what you learn. And the picture, the way this picture now is related to the previous picture is that the previous picture is like the slice along here.
Ah, okay. So then it can be thought of as a limit or what?
How to say?
Because in the end, you should say something about this.
But let me give an example. So if I begin with the point, well, microsheaves on the point, I want this to just be, you know, K mod. And from a point, I should produce some object whose sheaf category I compute and get the same. And the way I do it is I draw a point, and I push it forwards, push it up and down. And actually, in this picture, I just push them open, but let's also push them back closed. Okay, this is the rule. Or the way to say this rule abstractly is I take my Legendrian.
You should consider, yeah, okay.
I flow it forward and backward.
Yeah, you should consider the flow. All right, so you just explain how you construct this object, yeah.
I'm explaining how I make this object, and calculations similar to similar to the calculation that I did for the Unknot, although, you know, like a bit more sophisticated, will teach you what this microsheaf category is.
Yeah, okay, but actually I started asking long ago about this mirror symmetry story, but since you also mentioned this C star in complex setup, yeah, like C star scaled holomorphic symplectic form and all this 3D and equal 4 story. So your mirror symmetry, which you mentioned, like your paper with Ben and other, it's just conventional 2D mirror symmetry. Like Fukaya is equivalent to something else, and you replace Fukaya by whatever sheaves, micro sheaves supported on the core. But there is this 3D unequal 4 mirror symmetry, which is symplectic duality, which is completely, not completely, but it's different. So can you working with, in the complex setting, which you mentioned, you can see this symplectically dual stories. There is no gross Zibert or whoever.
I have never thought about the 3D mirror symmetry, so at least I can't do it. But, you know, it's good for someone to think about it.
Yeah. All right. Okay, there is a question from Pen. Pen, maybe you just unmute yourself.
Yeah, sure.
Okay.
All right, thanks.
Hey, good. Long time no see. Yeah. So the question is like go beyond, you know, the exact, the exact case. These authentic symplectic geometry can go beyond the exact symplectic case by considering deformations of Fukaya categories. But that seems to be a very global computation. You need to compute global disks that run through the divisor, and there may be very complicated bubblings involved. But on the other hand, these deformation categorically are just a deformation of some categories, and maybe you need to choose some nice direction of deformations. So the question is there any way to do a local to global computation for deformation as well? It's not related to the paper, sorry.
But it's I think it's related to GPS. Yeah, you cover by Weinstein manifolds.
But the answer. So let me say. So let me make a remark, which is that so deformations. This is deformations is about Hochschild cohomology.
Yeah.
And the Hochschild cohomology, and we're in the Calabi-Yau case, okay? So let me say that's the same as Hochschild homology.
Okay.
I mean, the situation for Hochschild cohomology is even worse, but let's stay in the CY case where it's about. And you know, in this kind of setting, we have some co-sheaf of categories. W on the skeleton.
Mm-hmm.
Yeah, maybe I don't call it W, because W is manifold on the skeleton. And you can consider the map from the Hochschild homology of and you can so you can ask, you can ask, is the Hochschild homology of F a co-sheaf? And the answer is the answer is very much no.
What if you replace the homology with chains? That's like a less.
I always mean chains.
No, it's commuting with homotopy colimits. It's something.
Yeah, it does not respect homotopy colimits. Everything inside, I always mean cochains, homotopy colimit, etc. And the answer is very much no. And in fact, but it is a pre-co-sheaf, and you could co-sheafify it. So you can consider the co-sheafification. And then you have a map from HH, this co-sheafification HHF. And there is a map from the global sections of this co-sheafification, maybe from the Hochschild homology of the global sections. Okay. And for example, did I get the direction right? For sheaves goes, there's a map. There's usually a map, other way. There's usually a map from the pre-sheaf to the sheaf, but for co-sheaf it's the other way. And so the example is when we take this original W is T star M, and this F is the constant co-sheaf. And in this example, what this map is the map from homology of M to the homology of the loop space of M. Okay, so all the, and in general, I mean, that's a theorem. The following thing is not, I think one could probably, we might be able to extract it from GPS, I'm not 100% certain, but in general, what's true is that this map is the map from the homology of W to the symplectic homology of W. Okay, so in particular, all the interesting deformations do not come from this local thing. That's not to say you can't approach those questions. It's just to say that you definitely cannot approach them purely in terms of that post-sheaf.
Yeah, but you know, like Vivek and Peng, you know this our approach to Fukaya with singular Lagrangians with Maxime, like 3 years old. When you complement before, you do not take the homotopy colimit of what you get from Weinstein domains themselves. First, you complement for each Weinstein domain, you complement it by something which sits outside of it, like combining with the symplectic field theory ideas with counting rep chords. So then whatever you do with a single Weinstein domain, you take into account possible large disks, as Peng mentioned, but before taking the colimit. So then you get some category which also knows about big disks, and only after that you take a homotopy colimit.
Yeah, I mean, you can define that, but the point is that you will never. But what I explained here is that that thing will never localize on the skeleton. And the proof is that the deformation.
Yeah, yes, of course, it will not localize on the skeleton.
Yeah,
but
I mean, you can define things that way, but if you wanted to think about how the deformation coming from outside interacts with the Fukaya category of the Weinstein part, you cannot think about it locally.
No, I cannot, of course. Yeah, but that's the whole point, because it cannot be defined in microlocal terms. That's what I was talking about, that there are large disks which this technique cannot.
So large disks you cannot cut into like small little pieces and glue disks. There's no
I mean,
technology.
Maybe you could do that, but you would, if you were going to do that, you would have to think about, I mean, what this explains somehow is that the thing that you just described is not a deformation of the local categories. You might be able to make more interesting local categories, which then you could glue to make, you know, something which deforms correctly. All I'm explaining is that with the ones that come directly from the microlocal sheaf theory, which I explained today, you couldn't do it.
Okay.
But let me make 2 more remarks now that I've written this on the paper. One is that what's called the algebraic Weinstein conjecture it says that I mean is the statement asserts that this map is never an isomorphism. And so the question of can you consider these deformations locally, not only somehow, I mean, the answer should be no, but in some sense, we don't understand things well enough to know that the answer is no, because I mean, this is an important conjecture. But what this, one outcome of all this discussion is that you can study this question about this algebraic Weinstein conjecture. It turns into a somehow question about when, under what assumptions about sheaves of categories can you enforce that this map is not an isomorphism? And so, of course, that, I mean, that's something one should think about.
Okay.
Okay, thanks.
More questions? It's the last chance. All right. If not, well, thanks, Vivek, for a nice talk and for a Q&A session, which lasts actually almost like the main talk. So could you please email me your notes so we can post them?
Okay,